Problem solving with projectile motion. Here's the problem. Imagine throwing a ball off the roof of this building, the Koch Center. How much time will the ball spend in the air? And how far out from the base of the building will the ball first bounce? The ball is thrown perfectly horizontally with a velocity of 10 meters per second, and the building is 20 meters tall. I want you to always first sketch the problem and identify the origin and which way positive x and y directions go. This need not be pretty. So here's a tiny person on top of a building and the path that I imagine the ball following. Note that I've shown it with a horizontal launch. Now I'm going to place the origin under the person on the ground level. This is convention, but not required. I've labeled that point 0, 0, 0 on the x direction, 0 on the y. Positive y and positive x directions go as shown. Now what I need to do is fill in my known values. Because the building is 20 meters tall, I set the initial y value to be 20 meters, the final y value to be 0 meters. Now I'm thinking about where the initial x, or what the initial x value is. It's 0 meters because that starting position of the ball is directly above the 0, 0, the origin point. Way out here at the end of the throw, I don't know the x position. In fact, that's one of the questions I'm being asked. I'm now going to model the problem to make sure I understand the motions. I'm going to show first horizontal part of the motion. Now, the biggest thing you got from the lab, the paradigm lab, was that horizontal motion and vertical motion are completely separate entities. The horizontal position is going to start at 0 and end at some unknown but positive value, and the motion horizontally will continue at a constant velocity. So my horizontal position graph is going to be linear. Let's move over to the vertical component of the motion now and draw that position graph. Let's see, my initial vertical position is 20 meters. My final vertical position is 0. I'm going to place some positions on this graph. And I know that vertically as the ball falls, it's going to accelerate. And specifically, it's going to speed up the ball. Now, the horizontal velocity of the ball is going to be constant but positive. And the vertical velocity of the ball is going to increase at a constant rate. The horizontal acceleration of the ball is 0. And the, wait, hang on, I screwed up the vertical velocity. Those are negative velocities. So I need to start at 0 velocity and end at a large negative velocity. My bad. That means the vertical acceleration is negative. And it turns out I actually know that number because, like in free fall, projectiles accelerate downwards at 9.8 meters per second squared. Now I'll just fill in that the horizontal acceleration is 0. And I'm going to annotate the diagram to just include that I know the vertical and horizontal accelerations. I tend to return to the diagram somewhat regularly while problem solving. Now let's describe this motion verbally. And now let's describe the vertical motion verbally. With our verbal descriptions complete, let's now switch to writing the equations. Now we're going to start with the horizontal position equation. The horizontal position is changing at a constant rate, so I need a constantly changing horizontal position. Now for the vertical position, one change you're going to see is instead of using x over here, I'm going to use y. And oopsie, my labels were swapped. So again, I'm going to use y in place of x to mean vertical position. Now that vertical motion is the accelerated motion change in position. So we're going to use the equation that ends in 1/2 at squared. I'm going to add some subscripts to these x's and y's so that I can help keep them straight when problem solving. My horizontal velocity is going to be constant. My vertical velocity, on the other hand, is constantly changing, so I'll use this equation. I'm going to return to the diagram because I realized something else that I left off is the initial y velocity starts off at 0 because we threw the ball perfectly horizontally. And then the other thing I need to add on here is that I actually know the horizontal velocity that was given to me. Now, my advice on setting up these problems is to next create two columns. First, we're going to solve for the amount of time the projectile takes to reach the ground. Both equations have time in them, but with the information that I currently know, the best approach here is to use the accelerated vertical velocity equation, which I'm just copy-pasting for my own convenience. The reason I picked this equation is I know everything except for time. Now, I know that the math teachers will tell you that there are two solutions to every square root. There's a positive solution and a negative solution. I'm not showing it here, but I'm rejecting the negative solution because in the context of this problem, it doesn't make sense. A negative 2 seconds would not have any meaning. So I've rejected that, even though mathematically I know it exists. The second half of my solution involves finding how far out from the base of the building the projectile bounces. This time, 2 seconds, is a useful quantity for me. Let me show you what I mean. The 2 seconds the ball spends falling to the ground is also the 2 seconds the ball spends translating horizontally. If I want to know how far, I need a position equation. Let's go grab that equation. And let's fill in what we know. Oh, right, I never wrote down that I know my horizontal velocity. It's constant everywhere across this diagram. And it's a constant 10 meters per second. The horizontal velocity is a constant 10 meters per second everywhere across this diagram. That's why I'm not attaching this label to any particular moment on the diagram, like I did with some others. Now, returning to the problem here, 10 meters per second times time. Shoot, I have two unknowns in this equation. And this is where I was highlighting earlier that 2 seconds is actually a known value for the horizontal motion. The horizontal position after 2 seconds of moving is about 20 meters. And that, my friends, is how you solve a projectile problem when launched horizontally. Good luck.